All right. Hey, folks. Welcome back to graphics. So we have a little bit to wrap up on the color lecture before we get on to image sensors. That's the main topic for today. So here we are. Here's where we left off last time. We were talking about color reproduction. That's the problem of trying to set the color on, or the specific version of the problem that we looked at was, how am I going to set the RGB pixels on my display, where those values are the intensity of the red, green, and blue pixels, right, physically in my display, to match some kind of spectral power distribution in the world S that I care about. And we solve the math. So if S is the spectral power distribution as, in this case, a column vector, then here is the math using the responses of the I for the short, the medium, long cone cells. And for the red, green, blue pixels in our display, these were the spectral emission curves for those to calculate the RGB values. Okay, so we left off here last time. We actually got through a couple more slides. We wrote this down, solved for this in an algebraic sense, and then I written a couple more slides down that I won't go over again because we did it last time, but I walked through some of the dimensions of these: solution form 1, 2, and 3. And I finished up talking about this last form, where we can also set it up in this way and actually recognize that this here, I didn't mention this last time or finish getting to this, but we can recognize this as the color matching functions from a hypothetical color matching experiment that we talked about a lot last time, where the color matching function in that case would be associated with the three primary lights, S sub R, S sub G, S sub B. So the red, the green, and the blue primary lights that we're using to try to blend together to match any test light. That's what's going on here, okay? This is a reminder that the way we got to color reproduction was talking about color matching. The color matching experiment is a perceptual, a psychological experiment, right? Where we ask a regular person to say when two colors are exactly the same, they can't tell them apart or not. And what they can do is they can adjust the brightness of the three primary lights to blend together three primary, or any number of primary lights in that case, but it turns out that 3 was a key number for normal color vision in order to match the test light. So you can think of what's going on here as, in choosing the RGB pixel at every pixel in your display, as a tiny color matching result of a tiny color matching experiment. Okay, at every point in the display, trying to match what? Trying to match the color appearance of something in the world, say a photograph, or some kind of piece of graphics, where at that point in the picture there's a certain color, and we're trying to match it. Okay, so this is the color matching experiment working, in your display millions of times every second, once for every pixel location. That's color reproduction in sort of a modern digital device kind of a setting. Now, there's one really important point that we've touched on before in the color matching experiment, and I want to come back to it here. It comes back again here in terms of what happens if we get negative numbers. The problem is, we can't have negative light, right? There's no such thing as negative light. So the RGB values that we send to a physical display must be positive, because they represent the physical amount of light, proportion of light that we want the display to emit at that pixel for red, green, or blue. So display primaries can't physically be negative, but the solution formulas that we just looked at in terms of linear algebra, in terms of matrix math on the previous slides, they can produce negative numbers, right? Okay, let's go back and take a look. Yeah, for sure. Okay, this input S here, this thing here, it's worth taking an exercise for yourself to convince yourself that there is absolutely no reason that these proportions here, or these dot products, will yield a positive RGB for every reasonable or every non-negative S input spectral power distribution here. So this formula will generate negative RGB values in some cases. So what do we do with that? I mean, what does that even mean if we get that in the solution formula? What it means if in the color reproduction formulas that we arrive at RGB, some negative RGB values in the solution is that the display won't be able to physically reproduce the desired color exactly. Okay, the desired color is going to be outside the display's color gamut. And so what does this mean? It's defining the color gamut, which is the physical space of colors that the display will be able to display, will be able to output. So what is a gamut exactly for, and how, that's the next topic for now. Okay, what's the gamut? What's the space of colors? Let me start with an example of what a gamut is. Okay, here are the color gamuts for two things. Okay, sRGB and Apple's P3. What is this? What are these exactly? These are color spaces that are commonly used for representing colors, for example, in certain file formats that are very common. And they're drawn inside this diagram here, which is some visualization of colors. So this sort of rough horseshoe shape that you can see here, along with this part down here. So there's purples down here, sort of cyanish here, bluish. This whole horseshoe shaped thing is something we're going to talk about the derivation of. This is a visualization for the space of colors that a human being can see, all the possible colors. So you can think of this as the color gamut of human vision. Okay, and there's two triangles in here that are drawn on top. There's this one sort of lighter that's labeled sRGB, and this is darker one, which is outside, which is labeled Apple P3, which is larger. Okay, so a gamut is just a set of colors. sRGB is evidently a color gamut that is smaller than P3. P3 is a wide color gamut, wide color gamut color space. Okay, and all points inside the triangles represent colors that can be represented in the gamut of those color spaces. Okay, so there's smaller and larger gamut color spaces. Now, in this case, these have primary colors associated with them, the definition of these color spaces. But before, where we talked about mathematically, you can combine any positive, zero, or negative linear combinations of the primaries mathematically speaking. That's true from a mathematical modeling perspective, but in color spaces, they constrain them to only allow non-negative numbers. Okay, so zero or positive that could be sent directly to a physical device. So color spaces have that constraint of non-negativity. So let's take a quick look and compare what sRGB and wide gamut P3 color spaces look like. Your mileage is going to really vary on this through Zoom. I sort of asked this, quizzed this in the past, and sometimes that was surprising to me. People could see this. Others, it was pretty invisible. So I'm going to describe what I see on my display, which is a wide color gamut display. And if you can't see what I'm talking about, I encourage you to go check it out on your phone or your laptop later in the PDF that, for the slides that'll be shared. Okay. Because usually those PDFs will include this color space in shallow and wide format gamuts. And your devices, if you have a smartphone that's reasonably recent, it will have the kind of extended color gamut physically that will show these differences to you. So let me start with this on the right-hand side. So what this shows is some kind of red image here. The left half is encoded in sRGB color space and has a narrower gamut of colors that it can show. And on the right is P3. So what I can see clearly on my display is that on the left-hand side, this looks completely like flat red, okay, in sRGB. But on the right-hand side, I can see there's a detail. There's some kind of circular icon here that's a little bit darker in outline. And then some icon that I can see here also outlined in dark. So the P3 color gamut is enabling me to differentiate different colors of red in that the sRGB cannot represent. Similarly, over here on the left-hand side in this picture of the yellow flower here, on the left-hand side, sRGB, I can tell it's yellow, but it looks far more brilliant, the yellow on the right-hand side in P3. And again, it's because the P3 gamut extends to a range of colors that is larger and encompasses a broader range of yellow colors in this case that my display happens to be able to physically reproduce, but that the sRGB format is not. The simple reason for this is that sRGB is an older file format from, if I recall correctly, from the 80s. And it was just at a time when physical devices did not have as wide gamuts as they do today. And so it would not have made sense to represent those wide color gamuts when no physical displays were able to display it. It would have sort of been wasting bits in the file format, in the file encodings, whereas today they can. Okay, so this is an example of physically what's going on. Okay, so some of you, great. Some of you can see this already through Zoom on the displays that you're looking at this on. If you can't, then as I said later, I encourage you to go check it out from the PDF on at least a modern, like a modern phone or something like that. Okay. What is the gamut? Let's get into details a little bit about how you calculate these things and how you represent them. So let me start by going back to this curve, which these are the response curves for the three types of cone photoreceptors in our eyes: the long, the medium, and the short wavelength cone cells. Okay, and all I'm showing you here is that we can go wavelength by wavelength. So here's one specific wavelength that I've chosen, and we're going to get, if you choose one wavelength, we'll get three values from these graphs, right? Just the three plot positions of the graphs for L, M, and S. If I choose a different wavelength, I'll get a different ratio, and so on and so forth. So I can imagine sweeping over wavelength, getting three values at every wavelength. And so I end up with a 3D curve in space is one way to interpret this, by sweeping wavelength and enumerating the L, the M, and the S responses here. I could plot that in 3D space. Let's do that. It'll look something like this. Okay, so now we just interpreted L, M, and S as the values for three Euclidean axes, three Cartesian axes. And as I said, we can start at 400 nanometer, that's over here, 450 nanometers over here, 500 is over here, and so on. It goes through 600 and then back to the origin. It starts at the origin because the origin is, ultraviolet and then infrared, which are invisible to us. So all three curves go to zero there, right? So of course it starts at the origin and returns to the origin when we trace it out in this way. And the curve roams through space in this sort of, interesting kind of a shape. Now, one thing to recognize, this is a very particular shape, okay? It's a very famous shape, it turns out. And it turns out it's a very fundamental shape in color science theory. And it's also very, it's a very deep curve because it's a very human curve, okay? Because it comes from the photopigment response functions. That's what these are. Those photopigment response functions are in the three cone cells in our retinas, and they come from three photopigments that code from, as I mentioned last lecture, three genes that are in our DNA. Okay, so this shape of this curve is encoded for literally in our DNA as human beings. We sometimes call this curve the spectral locus. Okay, it's just a name given to it. And the space of all possible responses that our visual system can receive, you can think of it mathematically as all possible responses or the positive linear combinations of points on this curve. Okay, now why is that? Well, if we get any particular spectral power distribution, we could mathematically sort of break it down wavelength by wavelength and say, well, how much is it going to contribute to the LMS response in our eye? And just integrate, right, over wavelength. So that would be like saying, okay, each wavelength, what's its response? It's going to be a combination of the power at that wavelength and then multiplied by the exact 3D location along the spectral locus curve for that wavelength. And so it's going to be a linear combination, weighted linear combination of the points on this curve. One way to picture all the positive linear combinations of points on this curve, like what's that shape in 3D space, is to picture this curve as sort of getting like plastic wrapped around it. I mean, literally the convex hull, okay, sort of wrapped around it. And then that three-dimensional shape blasted out into 3D space, which would sort of be towards us. Okay, this is the positive octant of 3 Cartesian space, projected out towards us, away from the origin, that 3D shape, okay? Now, if you think about that 3D shape that I just tried to describe, you'll notice a few things. It may not fill the whole positive octant of SML space, right? All the positive non-zero quadrant of SML as a Cartesian space, depending on the shape of the curve. And it definitely doesn't. If you stare at this curve enough, you see that, for example, look at the shape of this curve with respect to the M axis. Okay, here's the M axis. You got a label gamma there in this animation, but just think of it as M. So the shape of this curve goes out and never comes anywhere close to the M curve, for example. Again, the reason for that is because of the nature of the SML photoresponse curves that, again, are just a feature of our DNA. So there's very particular characteristics of this curve representing human color, response or human color gamut that flow from our DNA into the shape of this, the geometric shape of this curve. That's a bit hard to visualize in 3D space, what I talked about. So if you were having a bit of trouble with that, honestly, I have a bit of trouble visualizing 3D gamuts, almost everyone in color science does. Then what I'm going to show here, pay attention to this, because this might make it a bit easier to try to visualize a certain aspect of that color space, which is to project it into 2D, okay, of that color gamut. So how does this work? We take that shape that I was talking about before. It's this spectral locus and project it out into the positive direction away from the origin by linear combination. So the whole shape sort of projected out, and say, well, what happens if I want to project that onto a 2D plane? I could pick, as one example, I could pick a triangle that went from the S to the L to the M axis, okay? A triangle here, say at the unit level between S, L, and M. And then we could visualize it by looking back towards the origin from a vector that comes out, sort of the way that the camera position is, the camera's position here, say along the 1, 1, 1 vector direction, looking back at the origin. And we could just project the whole shape I described back towards the origin onto that triangle. If we did that, the shape that we get looks like this, okay? This is the spectral locus and its projections out into space, projected back towards the origin and then drawn here. Here's the S, the L, and the M axes. Now it's as a triangle because it's just drawn in perspective. The W point is the name for the white point. It's actually the origin of the spectral locus shape that we just looked at. Okay, and here you can see 440, 500 nanometer, 600, back to 700 nanometer. This is the shape of the spectral locus from before. The human gamut is here, shaded in light gray. Notice there's this whole section over here of S, M, and L ratios that is not part of the human gamut. So this graph literally means that you never see the M cones only stimulated by themselves in your retina. Mathematically, it's of course possible, but physically it turns out to be impossible. Basically because the M cone's response overlaps in the spectrum with the S and the L cone completely is the geometric reason for that. Okay. Anyway, so here's the human gamut. Here's a typical RGB display gamut drawn here. Okay, so that's where that sort of comes from. This, what I showed you before, is basically the same as the previous diagram geometrically. It's just a projection of that gamut down into 2D. It just turns out that this one is a really famous version of that, doing that linear projection into 2D. And it's extremely standardized. It's continues to be one of the most common visualizations of the human gamut, and for display gamuts overlaid on top of it. It's called the CIE 1931 little x little y chromaticity diagram, okay? Sometimes it's just shortened to chromaticity diagram. If someone says chromaticity diagram, they probably mean the standard version. All it is let me try to summarize it mathematically for you, is it's if you take LMS from before, and you do a projection, a 3x3 basis change into something called capital X, Y, Z. I'll come back to that in a little bit. This is an extremely standard CIE color space that was defined. Then, so it's nothing too mysterious. It's just a basis change from LMS Cartesian space to XYZ Cartesian space. Then we can define little x and little y. You can think back to the projective geometry math that we had earlier in lecture when our third lecture, when we talked about transforms. That looks like this. It's just capital X over the sum of X, Y, Z, and capital Y over the sum of X, Y, Z. We'll get little x, little y. This is little x here on the horizontal axis, little y on the horizontal axis here. Okay, we just draw it like this. So this is LMS drawn this way. This is little x, little y. You can see why the shape of this curve looks the same. Here's the horseshoe actually still here, okay? It just gets distorted because it's a transform, you can think of it that way, into this visualization here, and here is the horseshoe from before, okay? That's all that's going on in this particular visualization. But this is the most famous little x, little y visualization for chromaticity. I'm gonna talk a bit more about this here and give you a feature sort of walkthrough of this space. So On the outside, again, it's the spectral locus. If you had a laser light or a monochromator, a single monochromatic wavelength of light, it would have a color that's on the outside, the periphery of this spectral locus here. Runs from, say, 380 to 400 nanometers, all the way up to 700 nanometers over here. Notice that to make a color purple, there's no monochromatic light that will do that. That's a linear combination of like a monochromatic blue and a monochromatic red in order to make a purple. This is called the line of purples on the bottom of this chromaticity diagram. You can see sRGB drawn on here. NTSC turned out to have its own color space. There's a Adobe RGB here. I forget what this one is, CIE, it's sort of mislabeled. Oh, CIE RGB, CIE RGB is here. One way to read off the gamut and of any of these particular triangles, which represents the gamut from a color reproduction system that has 3 primary lights and is going through an additive or superposition color reproduction model, which is what we worked through the math for in detail last lecture, is to just look at the corners of the triangle, okay? What are the corners of the triangle? The corners of the triangle represent the position in chromaticity space for the specific red, green, and blue pixels in that color reproduction system. Okay, so for NTSC, for example, or Adobe RGB, here's the green, here's the red, and here's the blue that are used in those standards, okay? And then positive linear combinations ends up describing or allowing you to describe points inside the triangle. You could think back to barycentric coordinates for why positive linear combinations of the lights end up only allowing you to represent points inside the circle, inside the triangle rather, not outside the triangle of those 3 points. Okay, it's the same barycentric math, it turns out. Okay. So that's a description of color gamuts. That's a good transition to talk about color representation. Give me 1 second to catch up on. Oh yeah, look a couple good questions here. Let me go back and sort of clarify. So okay, so points inside the space. Someone asked a question with respect to this diagram on what the light gray means. That's the same question as what it means, and it might be easier for me to explain it here with respect to the interior points. The gray points on the previous diagram are the same geometrically, right? This is just a transformed version of that diagram, but now it's got a color rainbow drawn on top of it. It's analogous to points inside this horseshoe shape here that are color-coded. So what do points inside this diagram represent? It represents a color that's separated from the intensity of the light, or sorry, rephrase that, from the brightness of the light, or more formally, the luminance of the light. I'm going to formalize this in some slides in a little bit, but let me sort of mention it now. So if you could consider taking any color and sort of factoring out how bright it is, we'll sort of represent that with a number, and say, just give to me what the color components are. That's represented in this chromaticity diagram. So any spectral power distribution will project into some SML response, as we've talked about. And then the location in this diagram is representing the portion of the LMS response that has to do with color. What is the hue basically, and its position relative to the white point, which is kind of, as you can see in the center, and then how intense it is, how saturated it is. And the closer to the periphery, the more saturated the color is. The closer it is to the center where the white point is, the more desaturated it is. And the curve on the outside is, someone asked, is that the human gamut? Sort of. The entire space bounded by the convex hull of that outer curve is the human gamut. The human gamut is the space of colors we can see. So it's not only the outside, but everything inside too. That's a key conceptual point. The outside is the boundary of the human gamut, which represents the most intense, the most saturated colors that we can see. It's almost the full color of the rainbow. That's sort of where we get it. It's all individual wavelengths, except for purples. Okay, it turns out this sort of common fallacy that you can't actually get purple from a monochromatic light. So you have to have a linear combination of at least some red and blue. Someone asks, is it all triangles that cause the human eye? Are they all triangles because the human eye have 3 cones, or because the triangle barycentric coordinates are easier to calculate? Yeah, good question. It's a bit of both. It's a very good question. It turns out that, as I described, you need at least 3. in order to span colors reasonably for human to reproduce human color. It turns out that turns out to be an empirical fact. 2 won't cut it, right? You won't get anywhere near color reproduction, a reasonable result. So 3 is the starting point. And for various reasons, it turns out you can have more. So there are some color reproduction systems, for example, displays that might try to have red, green, blue, and then a cyan pixel or a yellow pixel. And then instead of a triangle, you would just have a polygon. And you get positive linear combinations of, or you can represent colors that are positive linear combinations of all of those primaries. The math is a little bit more complicated, but it's not, it's totally handleable, can be done from a engineering perspective. You can calculate those, but it is more expensive to have more pixel primaries. And the benefit of it is really diminishing after 3 is the way to summarize the engineering trade-offs there. Okay, color representation. The description of gamut sort of leads into a description as a more general concept of color spaces. What's a color space? We need to represent colors. We've talked extensively about how we need 3 numbers to specify a color because human vision is 3-dimensional empirically from the color matching experiment, which from a biological basis perspective comes from the fact that we have 3 photoreceptor types with 3 spectral responses of their own in our cone cells. But what 3 numbers to use? We've already looked at a bunch of different examples. LMS, I mentioned this XYZ thing. We've looked at RGB as an example for specific RGB pixels and had a bit of discussion about that. But this is a general discussion of color spaces. What 3 numbers should we use in our file formats to represent numbers? And a color space is an answer to that question. Okay, so a common example is display color space. We could define colors by what RGB scalar values we need to use to reproduce them on a specific monitor, a physical monitor. And this is the math, right, that we had used with, in this case, lowercase RGB, I guess. Lowercase being the spectra, RGB of lambda, and capital RGB being the scalar values, exactly like the color reproduction problem. So we could just say, hey, let's represent the color with those RGB values. You could do that. That'd be fine if you knew what these spectra are, but this makes it device dependent, right? So because it crucially depends on exactly these RGB spectra for my specific monitor that I've chosen to use for this display color space. And it depends on a few other characteristics of it too, like gamma, some technical topics that I've skipped over. But it's device dependent is the key issue. So if I choose RGB by looking at my display and I get it right, and then I send it to you, I send the RGB values to you, and you put it on your display, you may not see, in fact, you almost certainly won't see the same color as me because you won't be solving the same color reproduction problem. And some people are saying, well, that's why we need, display color calibration. We need display color calibration and also formalization through some kind of, color format interchange or color space, standard color spaces, basically, so that we can transact in color in a reproducible sense. Okay, so, sorry, let me keep going. I missed a couple of key points here I need to make. So for a specific display color space, we might also leave out some colors. There might be a limited gamut because the physical display will have a limited gamut. So for example, vivid yellow is an example that we looked at physically before. And this is because in file formats, the RGB or whatever the 3 numbers are usually constrained to be non-negative. Okay, I want to pause here and just sort of make a key distinction between sort of mathematical theory and then sort of computer science engineering representing bits and the trade-offs between that, and sort of reinforce for you 2 realities that are very important, exist simultaneously, but they have very, very different ramifications that are threaded through many of the things I'm teaching you today. One is that mathematically, representing color can be done exactly with 3 numbers. As long as you find a basis for the color, you can pick any 3 colors and take positive or take linear combinations of that in a mathematical sense, where you can have positive or linear combinations of that. That will form a basis, and that's from linear systems theory will span the full space of color in a representational sense. Exactly, the entire space, no compromises. what we've been talking a lot about is like, hey, with negative numbers, like physically you couldn't put it on a display, and then somehow it's leaked into our math a little bit. Okay, I just said here that the file format capital RGB is usually constrained to be non-negative and has a finite gamut. What's going on with that? It is not the same as the math. Okay, the math is linear systems theory math. You can have negative color values. It's theoretically pure. In file formats, the decision is made from an engineering perspective to not allow negative numbers. You don't just use a float, okay, and just encode it. You actually encode it with, fixed bits. And why do we do that? Well, think of it this way. Images are very expensive to represent, okay, compared to other data types. It's a very heavy format. We represent every pixel value. So because they're so expensive, the bits that we use to represent it, engineers take a lot of care to use those bits as effectively as possible. And so representing a whole bunch of negative numbers in the space is not a part of that. So it's constrained to positive values. And in fact, a finite has a positive, maximum value too. Like an 8-bit, for example, it's typical 0 to 255 for red, green, and blue. Okay, so that's the reason these file formats and the associated 3 numbers in those file formats ends up with these very tight constraints related to the gamut of that color space. So we could do, as I said on this slide, so I'm just go back for a second. We could have a display color space, easy to understand, but not very interchangeable. It's a small conceptual step to say we could standardize that. So that's what sRGB was the first famous example for. Little s stands for standard. Okay, so a bunch of companies got together at a certain moment and said, hey, all our displays are physically different, but we want them to be able to show the same colors, right, from files that people are sharing. So let's make a particular monitor RGB standard. We'll pick a device that's pretty close, a virtual device, to formalize the standard on that's pretty close to all of our devices that we know how to make. And other physical color devices will simulate that standard virtual monitor through calibration, okay? That way, all of us will allow people to share files, image files and colors through sRGB as the interchange color space. And displays will make up the difference to go from that through to what RGB values specifically need to be physically emitted from the display. sRGB is still widely used today, although there are other standards that are common now because it's not wide gamut enough as one of the primary driving reasons for evolution. I described one to you, Apple P3. There are others that have wider gamuts, okay? That's the main idea in it, though. It's really important. I'm going to tell you, though, that underlying the hood of this, for people that do real color science, historical norms are very strong, and there's a lot of code built on this, a lot of papers, a lot of science that's built on this. There's actually a historical standard color space called CIE, capital X, capital Y, capital Z. This comes from a long time ago. Oh man, I've forgotten off the top of my head. It's from the early 1900s, okay? To give you a sense of the depth of how long this stuff has been going on. And so this had an imaginary set of standard color primaries, capital X, capital Y, capital Z. It was designed so that capital X, capital Y, capital Z spanned all observable colors. So capital X, Y, Z can represent the entire horseshoe shape of the human color gamut that we looked at, okay, without a triangle insertion in the middle. It can represent everything, which is a good property. There are some other technical things. The matching functions were all strictly positive, which is sort of because of the kind of computation methods, human computation methods and constraints on that they had at the time. Another property is that the Y, it's just 3 values, 3 numbers. The Y, the middle value, was chosen to represent luminance. That's the brightness in the absence of color that I was saying before. So now the capital X and the Z encoded into, or the XYZ projected in, well, actually, let me come back to that. So that allows us to separate into chromaticity, which is the color component, and the Y, which is how bright, or the luminance. And it's an imaginary color space in the sense that you could never realize this, because it turns out that with this definition, the primaries have to be negative at some wavelength. So you could never build a display that had this. This is purely a representational file format, okay, or mathematical construct. The luminance, Y, again, was the lightness or the brightness of the scene. I mentioned this earlier when I mentioned photopic light conditions in the biological basis of color, a portion of last lecture. The Y is basically the response of the eye. If you could draw one, first, there's a green one here and then a black one. The green one is just in very, very dark conditions. Scotopic, which I might remind you is when rods were active. It's very, very dark, like dim moonlight. So pay attention to the black one, which is the more common case for our human viewing, which is the photopic, all the light levels that are brighter than that, basically. And this just asks the question, it's not a response for one of our cone cells, but it says, hey, if you tried to ask a person and test them on how bright do two lights look that are different wavelengths, what's the sensitivity of the eye? And it turns out people will tell you that the same power of light at 550 nanometer looks brighter than at 450 or 650 nanometer. And this curve here represents that. It's called the luminous efficiency curve. Sometimes for historical reasons, given the name V lambda, V of lambda, lambda being the wavelength. Anyway, luminance is just the V lambda curve, the sensitivity from a brightness perspective as a function of wavelength, dot product with a spectral power distribution. So I show you a spectral power distribution, you take a dot product with V lambda, and you can say, here's the luminance, okay? So that's the Y in the XYZ standard. So let's come back to capital XYZ. That was the definition for what that was before. The luminance is capital Y. You can define these chromaticities. This is a bit more general than I showed you earlier when I introduced this curve here. So let me just tie off the math in complete detail here. You can define little x, little y, little z as here, okay? Symmetric to the equations I showed before, but now with the z term. Since x plus y plus z equals 1, we only need to record 2 of these values, especially if we, we could have, for example, little x, little y, and capital Y as coordinates, the 3 numbers for a color space as an example. That would separate it into the luminance and then the chromaticity, sort of where the location is inside this, this chromaticity diagram that we have spent some time talking about. So this is really common, okay? Tell me the luminance, tell me the chromaticity as a way to separate the color in the historical capital XYZ, CIE XYZ color space representation. So I talked about this in some detail already before. This it's just another slide that reiterates that. One thing is clearer on this slide than it was before is there's, white is included in this space. There's sort of a point in the middle that's desaturated. The most saturated values are on the periphery, as we described before, monochromatic colors, at least in a, if you can make them powerful enough, which implies probably laser light. And then positive combinations of those, so spectral power distributions that contain combinations of those, linear combinations of those that are pretty balanced, end up producing colors inside the interior here, and a point in the middle here, typically at 1/3 by 1/3 as sort of a default choice, is called the white point, okay? There's a specific white that people perceive. Okay, but actually the white point is something that from the beginning of our discussion of color, you might be thinking, hey, Ren, but you told me about chromatic adaptation and how different objects that appear to us different colors actually have very different spectral power distributions when we look at them under different light sources. But, perceptually, they always look like a white piece of paper or a yellow banana or an orange to me, or a red apple. And so there's some standardization of perception or incorporation of that into color spaces, which is the next topic I want to share with you. Okay, so most color spaces don't take into account perceptual, perceptual organization. sRGB doesn't, well, a little bit, but it's not deeply in the design of it. CIE XYZ does not. CIE Lab is a color space that is a non-linear color space. Everything we've talked to up to this point is been a linear color space, okay, linear transformations from the spectral, the responses of the cone cells, the LMS. CIE Lab is nonlinear, and it was designed specifically trying to incorporate perceptual goals in the color representation, okay? So it's a perceptually organized color space that acts as a simple and useful color appearance model. Okay, what's a color appearance model? Let me try to share that with you and sort of define it as we go through here, but it's trying to tell us what is the actual color that we're looking at in this space in the world if I give you these coordinates. Some of the features of CIE Lab is that it incorporates chromatic adaptation, that effect that I showed you at the beginning, a very powerful effect that we're undergoing through all the time when we look at the world. You can think of it as related to white balance, right? The CIE Lab coordinates allow us to predict color appearance. To do that, there's something that uses an opponent color encoding. Remember the after images that I showed you at the beginning of this color lectures? The after image illusions that we looked at together, it uses that kind of perceptual and psychological theory of color in order to set up how to the coordinates, the numerical coordinates for this. And from those numerical coordinates, there are formulas for the hue, which is the red, green, blue, the color of the rainbow, the chroma, that's how saturated it is, a very saturated red or a not saturated red, and then the lightness, which is essentially the luminance that I described before. And then there's perceptual uniformity, which means that numerically, like if you assign bits into CIE lab space to represent the numbers with fixed precision, then linear steps, in that fixed precision, the goal is for those to correspond to linear steps in the change in perception of the color. Okay, that turns out to require a pretty heavy nonlinear warping. Okay, so I put this up here to show you there are formulas that define CIE lab. I'm not going to expect you to remember these numbers or almost any of you to have to calculate directly from them, but they're no mystery. You can get it directly off Wikipedia. This is an old science. It's a very old standard. This was defined in 1976. Okay, and they're pretty simple formulas. It fits on a page. Okay, there's a lot of details in the math here, some cube root powers and magic numbers. Okay, those have to do with attempting to reach the goals, the features of the goals that I described on the previous slide. So let me highlight a couple of things for you here. Okay, so it's derived from CIXYZ. So CIXYZ, as I said, is sort of like this very old standard color space. So CIE lab is defined by, first, if I give you some color in the world, calculate the CIE XYZ coordinates of it, then convert to CIE lab according to these formulas. Chromatic adaptation comes in here because we divide by the XYZ coordinates, the color coordinates of the perceived white point, the reference white point in the scene. Okay, so this standard actually requires you to go and say, hey, in this environment that we're taking these color samples from, a white piece of paper would have XYZ coordinates that are XN, YN, ZN. Okay, and for normalized, I guess, okay, or the reference white point. So we divide by them everywhere, and that sets reference white. And then and then the axes here are L star is the lightness. It's how black to white it is. And then A star and B star are the opponent axes. The color opponencies, remember from the after image things that we looked at, were yellow and blue were antagonistic and red and green were antagonistic in this after image hue that we looked at. There's a lot could be said on that. There's a very large literature in color science and vision science on that that's represented or taken advantage of in this color format. And so we have L star, lightness, A star, B star as the coordinates in CIE lab. Formulas for them over here. From L star, A star, B star coordinates, we can calculate like what an appearance is, what the color appearance should be. So how light it is, you can take directly from the L star. Is it very close to black? Is it very close to white? The chroma, the hue rather, which is the color of the rainbow, you can take it by calculating the angle around this circle here in this opponent axes that are drawn here. So it's the arctangent of B star divided by A star, okay, literally. And from that, the angle that you get, out of 360 degrees, for every one of those, it'll correspond to a color. So yellow and blue, obviously at these cardinal points in angle space, and red and green, but in between, yellow, green, cyan, purple, orange, those colors. Okay, so the angle directly translates to the expected color that you could name from a rainbow in that scene. And the chroma, C star, is the distance from the origin. So if it's a very small C star, you're close to the origin, it's very close to black and white. A very pale color or a colorless achromatic color, completely pure gray. And the larger C star is, the more out towards the periphery of the circle color it is, and the more intense the color, the more saturated the color, okay? As I said, the attempt is to make CIE lab perceptually uniform. CIE XYZ is not perceptually uniform. I showed you this diagram before. If you look closely before, you might have noticed that the overlay of this rainbow colors, which is, by the way, just a helpful visualization that color scientists have tried to do over the years, It's not inherent in this thing at all. It just is trying to give you a map of where colors are. You can tell it's not very uniform perceptually. There's a big area here that looks almost all the same green to me, a small area here that's all the same blue, a pretty big chunk over here that's orange that all looks the same. So this has been studied in perceptual studies to sort of try to tease out what's the density perceptually of this space in a famous study by someone called McAdam. The results are plotted on the left as McAdam ellipses. These ellipses sort of try to represent in this chromaticity diagram, the little x, little y chromaticity diagram, how large areas are that look perceptually the same. People can't tell apart colors inside them. And you can tell the ellipses are big over here. They're very small down over here. And so if you wanted to make this perceptually uniform, you'd have to perform some kind of nonlinear warping. People studied this a lot, okay? And they came up with simple equations that try to approximate that. CIE lab encodes that, okay? So the mapping from here to here, the attempt is to achieve perceptual uniformity so that linear steps in A or B correspond to linear perceptual steps. Yeah, it's getting a certain amount of color change for each of those steps. That's the same perceptual amount. That's the goal. Okay, and how is it encoded? It comes in this nonlinear function here, f, that's everywhere, that's defined here. Okay, people often say it's a cube root. It turns out this is a little bit hard to see. I don't have time to go through the details on it. Come chat with me in office hours if this floats your boat and you're interested in this. It's actually not a cube root in the perception. People often say, hey, the encoding of perception color, the perceptual nonlinearity is a cube root encoding. That's not actually true. It turns out the best fit to this is actually an exponent of not 3, but 2.43. So it's a bit of trivia, okay, for those of you that are interested in that. From a color science perspective, that's something that even experts sometimes get pretty confused about. Okay, last thing on color spaces, HSV, quite related in sort of concept to the things I've been talking about before, but mathematically very different to CIE lab. This is something that people sort of cook up instead of RGB to make it a bit more accessible for artists. It has a lot of the same principles. It ends up looking kind of similar to CIE lab, although the math is completely different under the hood. It's to define hue, which you can see is pretty close to the hue star that was defined previously. The saturation is a very intense color or a very pale color of that hue, and the value, which in this case is bright, value is meant to is brightness or lightness. So is it black or is it white? Okay, so HSV, sometimes called HSB in color pickers, that's what this refers to over here. And it just has the same kind of perceptual characteristics that I summarized for CIE lab. Okay, and I left out the math. If you're interested in it, you can look it up. It turns out that these are defined relative to RGB coordinates rather than from the CIE XYZ coordinates. But it's a very common color space, HSV, so I wanted to insert a couple of slides about that here as well. Last couple of slides on this. Color is a huge topic. We've covered a lot of ground in this introduction to it. One of the things that we haven't covered at all is additive versus subtractive color. So I just have 2 slides to at least highlight the issue or what the concept of it is. So we've talked completely about additive color. That's where we take 3, or any number of primary colors and we superimpose them in space somehow, almost like they're in the air. Okay, so if it's red, green, blue primaries, then mixing them gets us all to white, and subportions of them give us like yellow, cyan, and purple as an example. Subtractive color, which is actually mathematically better thought of as multiplicative color, although it's usually not called that, is really more like, you can think of it like paint or pigments. So in that case, you might have black and white paint or red, green, blue. And light that is arriving at it that is going to reflect off, part of that spectral power distribution as a function of wavelength will be absorbed preferentially. Black absorbs everything, white reflects everything, blue absorbs everything but the blue wavelengths or the short wavelengths, so on and so forth. This turns out to have a pretty different mathematical structure that's related to how you do printers. CMYK is sort of like a common file format here that I haven't touched on at all. So just to anchor this, additive color and beam colors, right, or superposition of colors, that's what's going on in the display in your phone or whatever you're looking at me on today in Zoom. The way the superposition happens and additive superposition is happening is, as a reminder, we have red, green, blue, tiny little pixels, but they're so small, they're so microscopic that we can't see them individually. So when we stare at them, they're mixing by blurring, basically, for that spatial location as are imaged by our eye. Okay, so the colors or the ratio of the RGB is being added up that way, superposition wise. That's beam color. Multiplicative color refers to like object colors. So if you think of like, oh, what makes, you know, the White Cliffs of Dover white, or in this case, the Seven Sisters, but I guess same as the maybe the Cliffs of Dover, maybe slightly more famous. What makes chalk look white? What makes sulfur look yellow? What makes cinnabar in this case look like this deep red mercury? It's because from it's multiplicative color. Okay, chalk essentially reflects all of the wavelengths that arrive it to a very high degree. Sulfur cuts out some of the short wavelengths, the bluish wavelengths, if you will. Cinnabar, you know, as you can see here in this graph of wavelength, absorbs a different sort of spectrum. Okay, so it's a whole theory around object colors that are related to pigments, paints, printing that we didn't talk about at all. We focus on digital color as expressed in devices of today. Okay, all right, and that's the end of our color lecture series. Let me just try to look back quickly over our chat. Let me try to take on some of the great questions that I see here. Okay, so Alexander asks, would the curve, the spectral locus curve, let me come back to it, see over here, would this curve be a little different for each person? You've got exactly the right intuition. Where would that variation come from? In a few different places, maybe the most important one being that there is a variation in the genes, the exact gene code for the photopigments, and that varies across the population. But it turns out there's pretty good agreement for quote unquote normal color vision. So that's why color displays tend to be, you know, pretty high quality across. If you ask most people, the color reproduction on displays is very convincing. That's the reason for it. But that variation in the extreme cases leads to things like color vision deficiency, like red-green color blindness. Okay, that's one of the most famous extreme versions of that variation, where the M and the L photopigments get very close together in their graph. But you're correct. This is not an absolute, and there is variation from person to person. There are other sources of variation too, but come talk to me in office hours if you'd like to go deep on that topic. Curves on the outside. It's the human. I answered those questions. Okay. Color calibration, HSV. Luminance already encoded in the gamut plot. Yeah. Oh, so luminance is factored out of this gamut plot. Okay. And the first time I introduced this, it wasn't clear yet until I defined CIXYZ. So now that we've gotten here, let me reiterate this point. Okay. CIXYZ is a standard. Okay. And you can get from LMS the CIXYZ by a 3x3 matrix transform, or directly from the matching functions that can be looked up on the internet, the numbers for those, to calculate from any spectral power distribution what the XYZ values are. From the XYZ values, you can define little x, little y, little z. If you keep little x, little y, that's this diagram over here. You need one more number to fully define what that LMS response was, right? The 3 numbers. So it's very common to keep y because it's intuitive. The capital Y then is how bright it is, and it's not at all represented. It's orthogonal to this chromaticity diagram. Okay, so little x, little y gives you the hue and the saturation, and capital Y, not shown here, gives you the how light, you know, how bright the color is. Okay. All right, very good. That wraps up our module on color. And with that, I'd like to move along and start our module on, or our lecture on image sensors. Just reshare. Okay. So our next topic is image sensors. This is a really cool topic, obviously really important. You know, each of us has multiple image sensors that are present in the devices we're using to see our faces over Zoom right now, or in your phone for lots of stuff that we do. let me start off with a little bit of, okay, why study image sensors? Obviously, it's ubiquitous. Here's a quick sparse random sampling to get your sort of, some common contextual, space for us all to think about the breadth of image sensor, impact today. There's imaging for robotics. This is Google's ARM farm, due in large part to Professor Sergey Levin. And this is an attempt to try to figure out how to get robots to be able to perceive things like a tray of stuff and pick them up directly from video, right? So there's a video camera up and above. So sensory motor actuation or perception and actuation of robots. Images were en masse, 15 million image databases with very deep categorization of the categories in them. This was ImageNet, right, which caused such a big breakthrough in computer vision in the pretty recent past, and has really transformed first computer vision and then AI. So imaging for computer vision continues to be critical to powering of that really important technology sector. Imaging and mapping is so crucial. It's in the news all the time now. Mapping, satellite imaging has been something that's really present in the news today to really inform, for example, what's going on in the Ukraine, and a lot of the terrible things that have been debated. What exactly is the truth have been separated out by satellite imagery just in the last 24 or 48 hours. But of course, it's been used before that for lots of things, like just trying to map what the terrain looks like for things like San Francisco, and incorporated, which is not trivial because you have to line all of this imagery and interpret it very accurately down to the positions of roads to enhance mapping technology at the street level too. So not just for overheads to understand navigation, but on the ground level to understand what you're likely to see when you're there. Special robots, of course, cars with imaging devices on them have been created in order to map all of this stuff. There's ubiquitous consumer imaging. Of course, we all have them these days. Action photography, drone photography. There's sort of continuing innovations, a frontier for how cameras with free viewpoint, with some mechanized component to position it in the right place, gets sort of pretty regularly innovated and disrupted in order to bring new consumer imaging experiences to the human population. There's imaging for virtual reality. This is a pretty recent result by Michael Broxton and a huge other number of collaborators, very famous collaborators at Google in this area of research and technology. This is just to interpret what this is sort of a big dome, a plastic plexiglass hemisphere in which a lot of holes have been drilled so that you can stick through the lens of like an action camera. I forget exactly what they used here. They might have been GoPros, quite a few of them. I forget the exact number. I'm going to say like, I don't know, 40 or something like that. Okay. And to do what is to capture a lot of video of some kind of scene from slightly different viewpoints from which you can try to synthesize, VR-like experiences. Technically, this was a 6 degree of freedom light field camera. Here's a short video clip that gives a sense of what you get. So from the device, which is sort of sitting at this location, after a lot of image processing, which involves 3D reproduction of the scene, 3D reconstruction of this scene from those multiple video feeds, then you can allow some change in viewpoint. It's a bit difficult to tell from the video, but you can sort of change to look at different angles. They may be more obvious. If you look closely, you might also perceive that you can actually, they're demonstrating a change in viewpoint from side to side as well, which is technically very difficult to accomplish. And in VR provides a very strong sense of immersion because we're very visually sensitive to that cue, which is called motion parallax. Okay, so a highly non-complete but sparse sampling of applications of imaging, right, in lots of visual computing related fields. So what's this lecture about? It's like boiling all the way down to the image sensor surface. Okay, we talked about cameras, lenses. That's not what's in this lecture. This lecture is about what's happening, at the sensor surface level. What are some of the issues that come up there in order to understand some of the key fundamental characteristics of real sensors, real photographs rather, and to understand some of the key limitations from an engineering perspective that you might expect to see from these systems if you try to actually build any of the applications that I described earlier, or other applications that you cook up in your future jobs. Okay, that's the purpose of this lecture today, or that we're starting today. Okay, so let's get right down to the basics. Image sensors are about photon capture. Okay, we talked about ray tracing, light sources, or putting out photon flux into the world. There's this flow of photons interacting with the world and materials propagating around. And then we have some kind of camera system. In this case, we're talking about not our eye, but we're talking about a real camera with like a lens. And then inside it, specifically, we're going to focus on digital imaging today. So there'll be some kind of digital image sensor inside there that is the device, the physical device that is recording that or measuring that photon flux rate and producing the digital numbers that are going into the pictures or videos that are coming out of the device. Okay, so photon capture is at the bottom of that stack. And where does it come from? It comes from a very famous crucial effect phenomenon for which actually Albert Einstein won his Nobel Prize. He didn't win it for general relativity or things like that. He won it for the discovery of the photoelectric effect. What's the photoelectric effect? The photoelectric effect says that if incident or describes the phenomenon by which incident photons, because they carry packets of energy, if they strike this a medium like a semiconductor here, then the physical device will eject electrons. This cartoon makes it a little fanciful, as if they go shooting off into space. That's not usually what happens. In the cartoon, is sort of like the free electrons are in the substrate and have free flow through the substrate. Okay, and by designing semiconductors, because all our chips are going to be based on CMOS technology, the same CMOS technology that we use in large part to create chips and memory, our processors and memory chips and things like that. We can create microstructures on the silicon in order to take these ejected electrons, these free charges, and then collect them during the duration of each picture, okay, or of each photo frame or video frame, for example. And they're going to be captured in tiny cells, spatially distributed over the surface. That's going to be our pixel structure. Okay, so that's the photoelectric effect. That's at the bottom. It can be organized into different kinds of devices that are fabricated in semiconductor fabs. Charge couple devices, or the class that came first, were very important for decades. Boyle and Smith won the Nobel Prize in 2009 for the development of the CCD, the charge couple device. This is a picture of a charge couple device. You can see it's in a semiconductor, packaging here. This is the surface. It's made on a big wafer, chopped up just like memories and processors. There's some stuff here I'm not going to get into the details of. There's a picture here that is the way CCDs work. That is a way to think about it. I'm actually going to skip this one. The picture is sort of self-explanatory. You can look at it later. I'm going to skip it because CCDs they hung on for a very, very long time, far longer than people expected, but really CMOS has taken over. It was long predicted to take over technologically, and it has. Okay, so all our devices and smartphones, all our imaging devices, our cameras and smartphones these days use CMOS sensors. There's a very large range of details in the design of these, just like there are a huge range of details at the semiconductor level for how you design memories or processors, but there's very common features for the designs of processors and memories, as well as for image sensors that are CMOS based. And so I want to try to share those with you. This diagram gets into one big high level concept, okay? CCDs are a very analog process that I chose not to dig into. CMOS is based more like a memory, okay, like a physical memory. A memory is sort of laid out in a 2D array, oftentimes on the chip surface. And so if you imagine that you lay out a memory where you can read from each individual cell, you need to be able to select which row it is and which column it is, and then you need to be able to read out the charge or the voltage at that memory location is the concept. That would be like a memory. If you could imagine that memory was laid out in a way where you're going to expose it to light, so that when light strikes it, the photoelectric effect can be happening, and it can actually knock free electrons that will then change the charge and therefore the voltage in each of these memory cells. And then after we finish that exposure, we say we're done. We close, for example, the camera shutter, so it's dark again, photoelectric effect stops, and we say, oh, I'd like to know how much light or how many photoelectrons were knocked loose in each of these memory cells. We can go and read off the memory cells one by one. That's a pretty good high-level conceptual model for what's happening in CMOS. Okay, so think of like a 2D memory laid out on the surface, photoelectric effect happening on it, stop the photoelectric effect by finishing a shutter duration, and then read out the memory cells. There's a lot of detail in designing those tiny memory cells so that they can do the work of collecting and maintaining that charge, not letting it spill out into all the neighbors, for example. There's a lot of logic that needs to be there for being able to address each of the memory cells. There's amplification that needs to happen for reasonable signal to noise ratios, or reasonably clean reading out of the voltages that are in there. So there's a huge amount of engineering at the semiconductor that's gone into this, and decades of iterative improvement in engineering over countless generations of CMOS sensors that have been put out into products in enormous numbers to optimize this. Okay. That's what leads to the huge numbers of variations in the details of this, but the underlying concepts that I've explained to you are a good mental model to have. In each pixel, so now we're looking at sort of a cross-section, a cartoon of some of the main typical structures you might expect to see in a CMOS pixel. One of them, think again of the CMOS sensor itself as a 2D array containing millions of these things, okay? There's a bunch of things. There's a potential well here, the silicon substrate, this is the semiconductor substrate, is down at the bottom here. This photodiode, this is actually where the photoelectric effect is happening, where the free electrons are being knocked loose. This potential well is a way to wall off the free electrons and capture that charge local to this pixel, okay? There's a bunch of transistors. Remember, this is the technology we use to make memories and chips. So we have transistors and all the kind of logic things that can be implemented in CMOS technology. You have to be able to reset the pixel, right? After there's some charge in there, you can't just take one photo and then have that sort of charge sitting around on the image and then take another picture. You just sort of get this sort of messy superposition of like all these pictures. You have to be able to reset it to zero, right? And very accurately in between. So there are transistors associated with that, transistors associated with setting, selecting this row or this column so we read out which cells we want later on. Amplifier, as I mentioned. There's also a color filter here, which I'm going to talk quite a bit about. We have to be able to put color filters on top in order to be able to take color photos. You might have pretty good intuition for what's going to be required from our color lectures already, but just know there is that structure there. We'll talk more about it. And then there's actually a micro lens on top of this too. So there's a bunch of interesting sort of micro optical things that are happening. This is not the lens at the camera scale to make like a global picture that we talked about with field of view and a depth of field and that stuff. It's not that lens. This is a tiny, tiny, tiny lens that sits on top of one pixel, and there's millions of these pixels and millions of these micro lenses in every CMOS sensor surface. A key figure of merit. Oh yeah, what does the micro lens do? Hold that thought. I'm going to come back to it. You can ruminate on it a little bit in the meantime if you like. There's a bit of a clue actually just in the picture here that might give you, send your mind in the right direction. I need some pictures later to really show you what the geometrical situation is in cross-section later to give you a sense on why this has turned out to be a really crucial technology implemented in all image sensors today, later on. A key figure of merit for devices is quantum efficiency. Quantum efficiency will depend on the device and how it inherently performs in all of its materials and the size of the transistors and how much light is funneled effectively into the photodiode and how much that is captured and kept free from noise sources and things like that. Quantum efficiency is the number of electrons that are eventually captured and then successfully measured later, divided by the number of incident photons at the device, in this case, the device being a single pixel. Human vision is actually not that high, but perception is awful good because of a whole bunch of other human visual system characteristics, but human quantum efficiency for human cone cells is maybe in the 15% sort of range. Smartphone cameras, maybe 60%. This number has actually really been optimized. I think this is a really low number these days. The most optimization has gone into smartphones, as you might imagine, for economic reasons. Back then, CCDs used for astronomy used to be greater than 90%. Scientific CMOS sensors, 95%. So it gives you a bird's eye view on what may be possible there. Okay, let me talk about color. So you might expect from the color lecture that in order to encode, color in our sensors, we're going to need to, we're going to need to have different shape different spectral response functions as a function of wavelength, and that intuition will be correct. So the way this works, I'm sure you've heard of it, is things called, for example, like the color filter. You may have heard of the Bayer color filter array. That's by far the most common and successful one. There are other variants too. This is a top-down look at the sensor showing many pixels and sort of the color filter pattern that is laid on top of neighboring pixels as a pattern. So you can get the pattern over here is RGGB as a repeating pattern for Bayer. This one has actually 4 color filters, REGB. You might say, Ren, I'm not quite getting that. I thought human vision is 3D. There's some stuff to do with color gamuts here, where you could get, there's a detection, there are gamuts for the detection side as well. And so E might give you a bit more color fidelity in certain parts of that gamut. I see even some designs that have completely white pixels, so there's no color filter over portions of them. And so you sample red, green, and blue sort of sparsely here, okay? Imran asked, what does the quantum efficiency of a device represent? The quantum efficiency is how well it's converting light through to electrons. Okay, so how much of the light that falls on it, how well is it doing in turning those into a signal that ends up in the files that we care about? If the quantum efficiency is high, it will make good looking pictures that are low noise. If it's low quantum efficiency, then it'll require a lot of light and will perform poorly, for example, in dark light conditions. Okay. There's a little comment down here. This is not the most crucial thing, actually. I'm going to skip over this in the interest of time, but this is how we get color layered into the sensors. I'm going to show you later some more detailed pictures of how the color filters actually look like in the arrays 3-dimensionally. But there's a little tiny color filter that goes in front of every pixel, and they're really tiny. So fabricating this is highly non-trivial. But it happens, and it's for neighboring pixels that this occurs there. Okay, so let me give you a bird's eye view on what's happening from a color perspective. So the sensor itself, right, the silicon has no idea whether something is red, green, or blue. It is modeled very accurately by the simple light detector model that I introduced 2 lectures ago. That was a detector that when photons fall on it, there's a fractional probability they will be detected. There's a fractional probability that the photoelectric effect will happen, basically, and that it will end up in the, captured accurately in the photon well for that pixel. Okay, so, and it'll be a function of wavelength, okay, because the silicon is more sensitive in some wavelengths than others. And so if you just had a silicon surface, you would end up with grayscale looking images, all right, that have to do with the inherent spectral response of silicon to the visible spectrum. Instead, we put color filters on top of each pixel. This is, of course, not what it looks like. It's this little cartoon to help visualize this little portion of this photo. These pixels originally are not color, they're just intensity values. And they're intensity values because there's a little red, green, or blue pixel that is blocking, right, part of the spectrum. So the color filter is doing what I alluded to at the end of that color lecture, is doing multiplicative color, right? The spectral power distribution comes through and the filter is absorbing some of that spectrum, absorbing out the blue, absorbing out the red, or absorbing out sort of the middle wavelengths in order to present something to the sensor surface, the silicon that is going to be tinted in color. Okay, so that's the principle. Now, note that at every pixel then from that silicon sensor in this color architecture, where we're putting a color filter array in front of each pixel, we don't end up with RGB per pixel, right? We end up with one of RG or B at each pixel. And in order to end up with RGB at every pixel that is in our file formats and that we display on our displays, we have to interpolate. Okay, so we have to interpolate this color in order to extrapolate, color fields that are full color everywhere. This is called demosaicing because the colors is in a mosaic pattern, and demosaicing is to take out the mosaic pattern in an algorithmic way. And the way you can think about it is interpolating sparse color samples across the image that we've captured into RGB at every output pixel. What's an algorithm for this? You could implement this already directly, using stuff that you had implemented in assignment 1. You could do bilinear interpolation. Okay, so for example, if you took the red color channel and you recognize that you have red at only these shown pixels and you want to find a red value everywhere else, you could start by just interpolating the color at every other cell from its closest neighbors using bilinear interpolation. That'll work. You could do the same for green and for blue. That could work, but it turns out it won't be the sharpest possible result. You'll end up with over blurring. You may also have more aliasing than's necessary. You could put your aliasing image processing thinking cap back on to sort of reason about why. In any case, for demosaicing, we need to do this. And so you can see 2/3 of the image data is going to be made up, okay, in this kind of a color architecture. Typical consumer cameras don't do this nearest neighbor or bilinear interpolation, as I mentioned, because it's not the highest visual quality. So they typically use more sophisticated techniques, such as interpolating and trying to avoid interpolating across edges. That's a pretty good starting point for algorithms that produce good results, okay? And that was how demosaicing algorithms worked in generations of cameras. These days, we're getting closer to the stage where demosaicing is happening in a more sophisticated way, data-driven way, using machine learning. So you could imagine trying to train some kind of system using a flexible machine learning CNN architecture with lots of input data of what the sensor data looks like and what the correct answer looks like, captured with maybe a higher quality camera or through some kind of simulation process. People have done that and shown that it's possible to squeeze out better results and avoid certain kind of artifacts, particularly aliasing artifacts that occur, without this. Okay. Okay. Very briefly, I want to mention that although almost all sensors in the world today use this mosaicing architecture because it is the one that has been most optimized and has worked out in a mass volume sense, okay? It is not the only way to produce color. There are ways optically that you could imagine doing it. You can build a device that just shows your white light coming in, separate it into red, green, and blue. It uses some sort of special layers called dichroic layers or interference layers that separate wavelengths of light out into bands in that way. And this is a diagram that I won't go into detail, but just the idea is the light comes in, and using that optical device there, you can separate it to use 3 different sensors, one of which will only sense red, green, or blue, and then you digitally put all the light together. So this is a way to capture without, sparsifying the red, green, and blue channels. There are actually other devices that are built. They're not very common, but it's a slightly different kind of CMOS sensor where the photodiodes or the pixels are actually stacked volumetrically. As you can sort of see here, the blues are on top because it turns out that blue photons, short wavelength photons, interact with silicon at more shallow depths. They're higher energy, so they tend to undergo photoelectric effect more quickly. And then green and red pixels are below. This is a way to stack it so that, again, you get RGB at every pixel location. It just turns out it was very hard to make this have very, very high performance in the fab for real built devices, even though the theoretical benefits are pretty compelling for this, but they were never competitive economically in terms of in terms of real world products that were built. Okay. All right. The next topic we're going to talk about, but we'll pick up on this next time, has to do with dynamic range in image sensors. Okay, so we'll just continue this on Thursday. All right, folks. Thanks a lot. Good to see you all.